Welcome to the Deep Dive, where we unpack complex topics and distill them into the essential insights you need to stay well-informed. Today, we're plunging into a foundational area for anyone building or designing modern vehicles, ISO 26262, specifically Part 4. We're going to give you a shortcut, sort of, to understanding product development at the system level, what it really means, why it's so crucial, and how it directly impacts the safety features we rely on every single day. Our mission for this deep dive is to provide a truly thorough explanation of this intricate stage, covering its activities, objectives, and, well, its profound significance.
That's right. This in-depth look is designed to bridge the gap from abstract functional safety concepts to the tangible engineering implementation. If you've ever found yourself grappling with how those high-level functional safety requirements truly transform into concrete system designs and real-world vehicle features, then this is absolute for you. We're going to walk through the meticulous process that ensures every safety-critical function in your car isn't just a good idea, but a rigorously engineered and exhaustively tested reality.
So let's unpack this. When we talk about product development at the system level, where does it actually sit within the broader functional safety life cycle? We hear a lot about the V model in automotive. How does this piece fit into that larger puzzle?
Well, if we connect this to the bigger picture, you should think of the V model as the bedrock, the foundational reference process for product development in functional safety. It's that classic, universally understood engineering framework. ISO 26262-Part, which is our focus today on system-level development, sits squarely in the middle of the left arm of this V. It's positioned after the initial concept phase, which is meticulously defined in ISO 26262-3. And crucially, it comes before the really detailed, in-the-weeds hardware development, which is covered in ISO 26262-5, and the equally complex software development, which is ISO 26262-626. So it's a pivotal link in the entire chain.
So it's not the very first step, but it's certainly not the last either. It really sounds like a critical translation point in the whole process, where the big ideas start to become much more granular.
Precisely. It directly follows what's called the functional safety concept, or FSC, which is generated in that earlier ISO 26262-3 phase. Think of the FSC as your high-level strategic roadmap outlining what needs to be safe. ISO 26262-4 then takes that roadmap and begins to detail the specific technical implementation.
Right.
So the FSC provides the crucial input, containing those essential high-level safety requirements. And then, in turn, this system-level development phase acts as the critical bridge, laying all the necessary groundwork for the detailed hardware and software development that branches off at the bottom of the V model's left arm. This stage also has direct ties to the integration and testing activities that occur on the right side of the V model, which is ultimately where everything comes together and is rigorously verified.
That makes a lot of sense. So how does the actual development flow within this system-level phase? Is it just a straightforward linear progression, or is there more to its internal dynamics?
It's definitely not a straight line. It's a highly iterative and often cyclical process. You begin by establishing what's called the technical safety concept, which essentially means integrating those technical safety requirements with the system's overall architectural design. You could picture it as sketching out the detailed blueprint for your safety-critical system.
Okay.
Once that initial architecture is laid out, those technical safety requirements, which remember were derived from the higher-level functional safety concept, are meticulously allocated to individual elements within the system. This allocation can even span across different technologies, whether you're talking about mechanical components, electrical circuits, or software modules.
So you're constantly refining and adding layers of detail, almost like zooming in on a map, getting more granular with each pass.
Exactly that. These requirements are refined, becoming progressively more specific and actionable. And importantly, new requirements often emerge directly from the evolving system architecture itself. One of the most crucial additions at this stage is the hardware-software interface, or HSI. This specification defines exactly how the hardware and software will interact, ensuring they work together seamlessly and, above all, safely.
The HSI, okay.
And for exceptionally complex architectures, the process of deriving requirements for subsystems might be even more iterative, demonstrating the inherent flexibility and continuous refinement embedded in the standard. It's a constant loop of design, analysis, and refinement, where insights gained at one level feed back to refine previous decisions.
So this phase really is the linchpin that sets the stage for everything that comes next, whether it's actual coding or the detailed design of circuit boards. It sounds like you absolutely have to get this part right. It's indispensable. This phase dictates precisely what needs to be implemented by both hardware and software. It's where abstract safety goals begin to take concrete, measurable form, guiding all subsequent detailed development. You simply can't hand a high-level safety concept to the hardware and software teams and expect them to magically make it safe.
Right.
Instead, you provide them with meticulously translated, detailed technical requirements. These requirements ensure that all functional safety objectives are clearly understood and thoroughly incorporated into the system's technical design before anyone dives into the specifics of either domain. It's about building safety in from the very foundation with clear, traceable, and defensible steps.
Building on that, once we understand its place in the V model, the first major output is defining this technical safety concept. But concept still sounds a little abstract to me. How does it truly translate those high-level functional safety ideas into actionable engineering? Yeah, that's a fair point. What's truly fascinating here is that the technical safety concept, or TSC, is essentially the aggregation of those specific technical safety requirements and the corresponding detailed system architectural design. It's truly the how-to guide that demonstrates why your proposed system design is actually suitable to meet the safety requirements derived from the functional safety concept of the FSC, while also intelligently factoring in any non-safety requirements and specific design constraints. It's where the rubber truly starts to meet the road, technically speaking.
Okay, so it's the detailed blueprint that says, here's exactly how we're going to achieve safety using this specific system with these specific components.
Precisely. Its core definition is the technical implementation of the functional safety requirements, or FSRs, but at a much more granular, hierarchical level. It takes into account the initial definition of the item, that's the system under development, and the proposed system architectural design. The whole purpose of the TSC is to provide that clear, logical rationale for why the chosen system architectural design is suitable to fulfill those safety requirements that originated in ISO 26262-Part. It explicitly addresses key aspects like how you'll actively avoid faults, how you'll detect those tricky latent failures, which are a very significant concern in functional safety.
Latent failures, right.
How you'll ensure safety integrity is maintained, and all the critical operational considerations throughout the system's life. And yes, the FSC is a direct prerequisite. The TSC builds directly upon those high-level FSRs, refining them into genuinely technical and implementable specifications.
And within this TSC, you're also building out the system's architecture itself. What critical considerations go into designing that system architecture effectively for safety?
A great deal of thought and rigor. The system architectural design is where you actually implement those technical safety requirements. This involves meticulous functional decomposition, breaking down the overall system into smaller, more manageable elements. For instance, if you're building a lane-keeping assist system, you decompose it into functional blocks like lane detection, driver intent monitoring, steering control, and human-machine interface. You have to carefully consider how these functions are distributed across various hardware and software components and, critically, how they will interact with each other in a safe, predictable manner.
And this is where safety mechanisms aren't just ideas anymore, right? This is where the actual ways the system protects itself are laid out.
Absolutely. This is where safety mechanisms are not just abstract concepts, but are concretely introduced and specified. Their fundamental purpose is to detect faults and then either prevent or mitigate failures that could potentially violate any of those functional safety requirements. The standard defines several types of safety mechanisms. For example, there's self-monitoring, where the system itself detects random hardware faults or even systematic faults within its own boundaries, things like communication channel failures or sensor drift. Then there are mechanisms dealing with interactions with external elements, like detecting faults in other electronic control units, power supplies, or communication devices that your system relies on. A major category is achieving or maintaining a safe state. These are mechanisms that contribute to the system reaching or staying in a predefined safe condition. And they include important considerations like arbitration for multiple control requests if different safety mechanisms are trying to take control simultaneously.
Okay, like deciding which system gets priority.
Exactly. You also need a well-defined warning and degradation strategy, outlining precisely how the system will inform the driver of an issue and how it will degrade gracefully to a safer state rather than failing catastrophically. Think of it as a controlled shutdown or a reduction in functionality rather than a total loss.
And what about those tricky latent faults you mentioned earlier? How are they addressed at this stage?
Latent faults are a critical concern, often the quiet threat that keeps engineers up at night. These are faults that exist but aren't immediately detected, and they can combine with other faults later to cause a dangerous situation. Imagine a small, unnoticed crack in a bridge support. That's the latent fault. By itself, it doesn't cause a collapse. But if a heavy truck drives over it later, another fault, the two combine, and the bridge could fail.
Right, I see. That makes sense.
So safety mechanisms are also specified to prevent latent faults from remaining undetected. This often involves rigorous self-tests that run during power-up, continuously during normal operation, during power down, or as part of maintenance routines. It's actually a firm requirement for ASIL C and D systems, the higher automotive safety integrity levels, to have mechanisms specifically for preventing latent faults. These are about uncovering those hidden weaknesses before they can team up with another failure to create a hazardous event.
So for each of these safety mechanisms, are there very specific parameters that need to be defined beyond just what they do?
Yes, absolutely. Especially for mechanisms that are designed to lead the item to a safe state, you must specify the precise state transitions, including how they will control actuators. For our lane keeping assist, if a critical sensor fails, the TSC would specify how the system disengages steering control, provides a warning to the driver, and transitions to a LKA unavailable safe state. You also define the fault handling time interval, or FTTI, which is the maximum time allowed for the system to detect and respond to a fault and transition to a safe state. This FTTI is crucial. It's a strict deadline. If for some reason the safe state cannot be reached within that FTTI, you then need to specify an emergency operation tolerance time interval, which essentially defines how long the system can operate in a degraded but still controlled manner before absolutely having to reach that safe state. These time intervals are often derived from the hazard analysis itself.
And how does all of this feed into the overall diagnostic strategy for the system?
It's integral to it. For multiple point faults, where several independent faults could combine to cause a safety violation, a detailed diagnostic test strategy is crucial. This strategy considers the reliability of hardware components, their role in the architecture, and how they might contribute to such a multiple point failure. It also factors in the quantitative target values for safety goal violation from ISO26262-Part, the assigned ASIL, and the specific multiple point fault detection time interval. These strategies can be time-driven, like periodic tests running every few milliseconds, or event-driven, like a diagnostic test that runs only at system startup. What's also very specific in the standard is that the development of safety mechanisms that are implemented only to prevent dual-point faults from being latent must comply with specific ASILs themselves. For instance, if the primary technical safety requirement is ASIL D, the mechanism preventing latent faults might need to be developed to ASIL B. For ASIL B and C primary requirements, it's ASIL A, and for ASIL A, it's QM or quality management. This clearly shows the hierarchical nature of safety integrity and how the standard dictates the rigor applied even to the mechanisms that protect against hidden failures.
And all of these requirements eventually need to be assigned to either hardware or software, right? How does that ASIL allocation work, especially when components might serve multiple functions?
That's right. It's a critical and often complex step. Technical safety requirements are meticulously allocated to the system elements, specifying whether they will be implemented by the system itself, by hardware, or by software. A key principle here is that each element then inherits the highest ASIL from the requirements it implements. So if a single hardware component, let's say a microcontroller, is responsible for functions with different ASILs, perhaps an ASIL D lane keeping assist function and a QM level infotainment function, that microcontroller must be developed and treated according to the highest ASIL.
Which would be ASIL D here.
Correct, ASIL D in this case. This applies unless specific coexistence criteria, as defined in ISO26262-Part, are met, which allow for separation. This rule ensures that the most stringent safety requirements drive the development and verification of that element, preventing any compromise.
This sounds like where the hardware-software interface, or HSI, becomes absolutely vital. Can you elaborate on that and maybe give us a tangible example of why it's so important?
The HSI specification is truly fundamental. It details the precise interaction between the hardware and software, ensuring absolute consistency with the technical safety concept. It's not just a general description. It delves into the specifics of how the software controls hardware components and utilizes hardware resources. Think of it as the shared language and rulebook for how these two domains communicate to achieve functional safety. Without a clear HSI, you're essentially asking two highly specialized teams to build a bridge from opposite sides without agreeing on the design or even materials. The results would be, at best, inefficient and at worst, unsafe.
So what kinds of specific characteristics would be detailed in an HSI for something like our lane keeping assist system?
It encompasses a wide range of critical characteristics. For our LKA, for example, it would specify the relevant operating modes and configuration parameters for the steering actuator hardware, things like its default state, any calibration modes, or even specifics like the gain control settings for its motor. It also defines hardware features that are designed to support independence between elements or to enable software partitioning, which is crucial for preventing interference between safety-critical LKA functions and, say, a non-safety critical heated steering wheel function.
Partitioning, okay.
Then there's the clear definition of shared versus exclusive use of hardware resources, like memory mapping, allocation of registers, timers, or I/O ports. It outlines the access mechanisms to hardware devices, whether they are serial, parallel, or master-slave communication. And importantly, it details the timing constraints that are directly derived from the technical safety concept, ensuring operations happen within specified timeframes. For instance, the HSI would state that the LKA software must read the steering angle sensor data and send a torque command to the actuator within a certain number of milliseconds to ensure a timely safety response.
And what about diagnostics? How does the HSI play a role there?
The HSI is also the place where the relevant diagnostic capabilities of the hardware are specified, and critically, how the software will utilize these features. This includes defining hardware diagnostic features themselves, such as detection of overcurrent, short circuit, or over-temperature conditions within the steering actuator. And then it details the specific diagnostic features concerning the hardware that need to be implemented within the software to monitor those hardware conditions.
Right.
Annex B of the standard provides some excellent examples of HSI elements and characteristics. For instance, HSI elements include memory types like volatile and non-volatile RAM, various bus interfaces like CAN and LIN that connect the LKA ECU to other parts of the vehicle, AD and DA converters for sensor inputs and actuator outputs, multiplexers, electrical I/O for switches, and even internal and external watchdogs for monitoring system operation.
Wow, quite a list.
And as for HSI characteristics, you're looking at things like interrupts for time-critical events, ensuring timing consistency across the system, data integrity to prevent corrupted sensor readings, detailed initialization procedures for memory and registers at power-up, boot management, message transfer protocols, network modes like sleeping and awakening, memory management including reading, writing, diagnostic access, address space, and data types, and also real-time counters. All of this ensures a precise, controlled, and verifiable interaction between the hardware and software for safety.
That is an incredible level of detail. And finally, for this segment, how are system safety requirements, or SSRs, and interface safety requirements defined?
System safety requirements are derived directly from the functional safety concept, and then further refined based on the detailed system architectural design. They precisely specify the stimulus response behavior of the system that directly affects safety. For our LKA, an SSR might be, upon detection of driver hands-off for X seconds, the system shall gradually reduce steering assist to 0 within Y seconds and issue a visual and audible warning.
Very specific.
Exactly. In parallel, external interface specifications are absolutely crucial. These ensure that other elements that interact with your system but might not be part of your safety-related item, like, say, the vehicle's general power management unit or infotainment system, do not adversely affect the safety-related elements within your system. And a very important point, if your system implements other functions or requirements in addition to the safety-critical ones, these non-safety requirements must also be clearly specified or referenced, and they must not contradict any of your technical safety requirements. It's about ensuring harmony across all system functions, with safety taking undisputed precedence.
So we've painstakingly built the blueprint. Now here's where it truly gets fascinating. How do we find potential flaws in that design before we even build anything? What kinds of safety analyses are we talking about at this system level, and what makes them so powerful? This really seems like the ultimate measure twice, cut once approach, but on a massive scale.
That's an excellent way to frame it. This raises an absolutely critical question. How do we proactively ensure safety? It's simply not enough to just design a system. You have to prove, through rigorous analysis, that it will meet its safety objectives. Safety analyses are absolutely integral to the system architectural design process. They're performed to provide concrete evidence that the design you've meticulously put on paper is suitable for its intended safety-related functions, to identify the root causes and potential effects of faults, to confirm which elements are truly safety-related, and crucially, to verify the effectiveness of the safety mechanisms you've designed. Think of it as stress testing your blueprint before you ever lay a single brick or write a line of code. These analyses are truly intended to assist in the design process itself, providing invaluable feedback for continuous refinement.
So it's not just a post-design check, it's an iterative design tool.
Mhm.
What are the key methods used for these analyses, and how do they differ?
Precisely. You can't wait until the end. There are primarily two key categories of safety analysis methods at the system level: deductive and inductive. Deductive analysis, beautifully exemplified by fault tree analysis, FTA, starts from an undesired top event, typically a specific system failure or a safety goal violation. For our LKA, this top event could be unintended steering intervention leading to vehicle exiting lane. You then work backwards systematically, identifying the various combinations of basic faults or events that could logically lead to that undesired top event. It's like peeling back the layers of an onion to find all the potential root causes. The standard highly recommends FTA for ASIL C and D systems, and it's recommended for ASIL B. This is because for higher ASILs, you need that deep, top-down understanding of every single failure pathway.
And the other type?
On the other hand, inductive analysis, typically done through failure mode and effects analysis with diagnostic analysis, FAAD, starts from potential component failures and works forward. You identify a specific component, like the camera sensor in our LKA, consider its possible failure modes, figure stuck at value, intermittent output, no output, and then determine the effects of that failure on the system and ultimately on safety. So if the camera sends a lane visible signal when the actual lane markings are faded, what's the effect? FMEAD is highly recommended across all ASILs A, B, C, and D because it's a very systematic way to identify potential single-point failures and their consequences.
That makes the distinction really clear. You also mentioned dependent failure analysis earlier. How does that factor in here, and why is it so important for complex systems?
That's an excellent follow-up, and DFA is absolutely critical because it specifically addresses common cause failures or cascading failures. Well, dependent failure analysis, or DFA, isn't explicitly listed as a primary method in the standards table for system architectural design analysis. The document does mention analysis of common limit conditions, sequences, and sources of dependent failures as a method for deriving test cases later on.
Oh.
And the foreword to the standard provides additional guidance on dependent failure analysis. DFA is all about ensuring that a single fault or event doesn't trigger multiple, seemingly independent failures across different elements that were actually designed to be independent. You're looking for hidden dependencies that could undermine your entire safety architecture.
Like a chain reaction.
Exactly. For example, if both the camera and the steering ECU in our LKA system share a single non-redundant power supply, a failure in that power supply could be a dependent failure, simultaneously disabling both safety channels. Or if two independent software modules communicate via a single shared memory area, a corruption in that memory area could cause a dependent failure. This analysis forces engineers to uncover those subtle, unexpected interdependencies.
So once these analyses are done, how are the findings actually used? Do they just sit in a report, or do they actively shape the design?
They're used in several crucial ways, and they absolutely shape the design. First, both deductive and inductive methods help in identifying potential failures throughout the system architecture, pinpointing exactly where vulnerabilities might exist. Second, by thoroughly understanding the causes and effects of these faults, development teams can assess the residual risk. This means evaluating how effective the proposed safety mechanisms are in mitigating those identified risks and whether any unacceptable residual risk remains.
And if it does?
If it does, the design must be revised. It's a non-negotiable feedback loop. And third, these analyses directly support verifying the effectiveness of safety mechanisms. It's not enough to say we have a watchdog timer. You use FTA or FMEA to confirm that the watchdog, as designed in Clause 6, will actually detect the faults it's supposed to and prevent the hazardous outcome within the specified FTTI. It's about proving the design works, not just hoping it will.
Beyond just identifying random failures, how does this part of the standard address preventing systematic failures, those design flaws that aren't random but inherent to the system?
That's a critical distinction, and it's where a lot of the standard's genius lies. Systematic faults are inherent in the design, the process, or even the manufacturing. They're not random. If you have a software bug, it will manifest consistently under the same conditions. To reduce their likelihood, ISO26262-Part emphasizes applying well-trusted design principles. This includes the reuse of well-trusted safety concepts, proven designs for elements including hardware and software components, and leveraging well-trusted mechanisms for failure detection and control. Standardized interfaces also play a big role in reducing systematic errors.
Right.
The system architectural design itself should exhibit modularity, an adequate level of granularity in its breakdown, and simplicity. This can be achieved through hierarchical design, precisely defined interfaces, actively avoiding unnecessary complexity, and ensuring the system is maintainable and verifiable. This proactive approach aims to build robustness into the design from the very beginning, catching potential systematic issues before they become deeply embedded.
And what if new hazards pop up during these analyses that weren't identified earlier in the project? Does that send you back to square one?
That's a key feedback loop, and it highlights the iterative nature of functional safety. If any new hazards are identified during these detailed safety analyses, or even during the system architectural design process that aren't already covered by existing safety goals, they must lead to an updated hazard analysis and risk assessment, HAR, from ISO 26262-Part.
So you update the HARA.
Yes, this demonstrates the dynamic nature of the functional safety lifecycle. Findings from later stages can and should feed back to refine earlier outputs. It's not about going back to square one in a bad way, but rather refining your understanding and ensuring all risks are accounted for. The standard also clarifies that while non-functional hazards might be identified, like those related to cybersecurity, only those directly causing malfunctioning behavior of e-safety-related systems fall within the scope of ISO 26262. However, they can still be annotated in the HAR report for completeness.
And what about controlling random hardware failures? How are those measured or addressed at this stage before you even have physical hardware?
For random hardware failures, specific measures for detecting, controlling, or mitigating them are specified based on the architectural design. An example would be defining how specific hardware diagnostic features, like built-in self-tests within a microcontroller or error-correcting code in memory, are to be utilized by the software to detect random hardware failures. For ASIL B, C, and D, which are the higher ASILs, specific target values for failure rates and diagnostic coverage are specified at the element level. This directly aligns with the more detailed hardware-level requirements in ISO 26262-5, Clause 9, ensuring that the system-level design sets concrete, measurable goals for hardware reliability and diagnostic capability. This is a crucial quantitative aspect of safety, ensuring that you're not just designing what to do, but setting measurable targets for how reliably it must do it.
So we've designed the system, analyzed its potential flaws, and refined the blueprint. Now, how do we make absolutely sure it actually works as intended? This is where verification and testing come in. What's the approach here at the system level, and what's the crucial distinction between verification and validation?
This is truly where abstract concepts transition into tangible, demonstrable evidence. It's the point where you systematically prove that what you intended to design is what you've actually built, and that it works as expected. The distinction you mentioned is fundamental. Verification ensures that we've correctly implemented the requirements, essentially asking, are we building the products right according to our specifications?
Okay.
Whereas integration testing confirms that all the pieces work together as a cohesive, safe unit, answering, are we building the right product, one that actually fulfills its safety goals?
Let's start with system-level verification, then. What are its main objectives and activities?
The primary objective of system-level verification, detailed in ISO 26262-4, Clause 6.4.9, is to provide clear, auditable evidence that the technical safety requirements are correct, complete, and consistent. It also aims to confirm the overall suitability and adequacy of the system, architectural design, the hardware-software interface, HSI specification, and the entire technical safety concept in achieving the required ASIL. The activities involve meticulously verifying those technical safety requirements, checking for their correctness, completeness, and consistency against the defined boundary conditions of the system. You also verify the system architectural design itself, the HSI specification, and any requirements related to production, operation, service, and decommissioning, as well as the overall technical safety concept. It's a thorough check of all the design outputs from this phase.
And how do they actually do this verification? What specific methods are used to achieve this level of assurance?
The standard provides specific, well-defined verification methods. Inspection is highly recommended for all ASILs. This is essentially a detailed, systematic review of documents like design specifications, code, or diagrams by experts to identify any errors or omissions.
Like a peer review?
Sort of, yes, but often more formal. Walkthroughs are highly recommended for ASIL A and recommended for ASIL B, where a team collectively steps through the design or requirements as if executing the system, identifying issues in a collaborative manner. Simulation is highly recommended for ASIL C and D, and recommended for ASIL A and B. This can be used for modeling complex system behavior and is particularly powerful for fault injection, where you simulate faults to see if your safety mechanisms respond as intended.
Injecting faults, okay.
Similarly, system prototyping and vehicle tests are highly recommended for ASIL C and D, and recommended for ASIL A and B, allowing for early, real-world testing in a controlled environment, also enabling physical fault injection. And of course, the system architectural design analysis, which refers back to the safety analyses we just discussed, is a core verification method. It's about combining these different approaches to build confidence from multiple angles.
So once the individual parts and designs are verified, then comes integration, right? How does system integration testing work across these different levels?
Yes, that's the next critical step, covered in ISO26262-Part Clause 7. The overall objective here is to define the various integration steps, progressively integrate system elements, verify that all of the defined safety measures are properly implemented, and ultimately provide evidence that these integrated elements truly fulfill their safety requirements. The general approach to integration is systematic and hierarchical. It starts with hardware-software integration, then moves to system integration, and finally to vehicle integration. Tests are performed rigorously at each stage to ensure everything works together correctly and, most importantly, safely. This multi-layered approach helps pinpoint issues at the earliest possible stage.
And what's the strategy for these integration tests? How do you ensure you cover every possible scenario?
A comprehensive integration and test strategy must be defined up front. It's designed to check the correct implementation of both functional and technical safety requirements, the functional performance, accuracy, and timing of safety mechanisms, the consistent and correct implementation of all interfaces, and the system's overall robustness. This strategy must cover the entire integration subphase, ensuring that every single safety requirement is verified at least once across all the testing stages.
Wow, every single one.
Every single one. To enable the appropriate specification of test cases, they are derived using a combination of methods. These include detailed analysis of requirements, external and internal interfaces, generation and analysis of equivalence classes, boundary values, testing at the limits of operation, error guessing based on expert knowledge and past failures, analysis of functional dependencies, analysis of common limit conditions and sources of dependent failures, various environmental conditions, operational use cases, and even analysis of field experience from similar systems. It's an exhaustive approach to test case generation.
Let's break down those layers of integration, starting with hardware-software integration testing. What does that specifically entail for a system like our lane keeping assist?
In hardware-software integration and testing, Clause 7.4.2, the hardware developed according to ISO26262-5 for our LKA, that would be the steering actuator, the camera sensor, the ECU's microcontrollers, and the software from ISO26262 are brought together. The tests at this stage primarily verify compliance with the HSI specification we talked about earlier. So does the LKA software correctly read the camera data via the HSI? Does it send the correct commands to the steering actuator via the HSI? And do those commands have the intended physical effect?
Checking that handshake, essentially.
Precisely. The key test goals include ensuring the correct implementation of technical safety requirements, verifying the functional performance, accuracy, and timing of safety mechanisms, like the watchdog timer checking the software execution, confirming the consistent and correct implementation of interfaces, assessing the effectiveness of hardware fault detection mechanisms, and checking the overall robustness of the HW-SW interaction. Methods employed include requirements-based testing, fault injection testing, which is particularly useful for verifying safety mechanisms by introducing faults during runtime.
Like shorting a wire.
Exactly. For instance, shorting a sensor line to see if the software detects it. Back-to-back testing, comparing the integrated system with a simulation model, performance tests, and various interface tests, external and internal, as well as resource usage and stress tests to push the system to its limits.
And then when those elements are successfully integrated, you move to system integration. How does that differ, and what new challenges does it address?
Correct. System integration and testing, Clause 7.4.3, involves integrating the individual elements of the complete system according to the system architectural design. So for our LKA, this would be integrating the LKA ECU, not just with its direct sensors and actuators, but with other vehicle systems it needs to interact with, like the vehicle speed sensor, the braking system, or the driver information cluster. The test goals here are similar to HWSW testing, but are applied at the broader system level, focusing more on how the integrated elements interact and behave as a whole. A crucial addition is the coverage of failure modes at this level, ensuring that all identified failure modes from the safety analyses are tested.
Covering all the known failure possibilities.
Yes, Beyond the methods used in HWSW testing, system-level testing also includes specific tests for interference resistance and robustness under certain environmental conditions, like EMC, electromagnetic compatibility, and ESD, electrostatic discharge tests, which are absolutely vital for automotive environments where electromagnetic noise is prevalent.
And finally, the ultimate test, putting it all into the vehicle itself.
That's vehicle integration and testing, Clause 7.4.4. Here, the complete item, your fully integrated LKA system, is brought into the vehicle and integrated with the rest of the car. A critical activity is verifying the item's interfaces with the in-vehicle communication and power supply networks. Does the LKA system correctly interpret messages from the vehicle's CAN bus? Does it draw power reliably without interfering with other systems?
Making sure it plays nice with others.
Exactly. At this highest integration level, test goals include confirming the correct implementation of functional safety requirements at the vehicle level, validating the functional performance, accuracy, and timing of safety mechanisms. e.g., does the LKA disengage within the FTPI when the driver overrides it in a real car? Ensuring the consistency and correctness of both internal and external interfaces, item to vehicle, item to environment, and assessing overall vehicle robustness under real-world conditions. What's unique here, beyond requirements-based testing and fault injection, are long-term tests and user tests under real-life conditions. These involve larger sample sizes and normal users, operating the vehicle in everyday scenarios, not just predefined test cases. This provides invaluable real-world validation that laboratory or HIL simulations simply cannot fully replicate.
So we've distinguished verification, did we build it right, from integration testing. But then there's a final, seemingly distinct step. Safety validation. What's the distinction there, and what's its ultimate purpose?
That's a crucial distinction. While verification checks if the product is built correctly according to specifications, safety validation confirms that the product actually achieves its safety goals and is appropriate for its intended use in the target vehicle. It provides the ultimate evidence of functional safety, asking, did we build the right product for the intended purpose, and is it truly safe in the real world? The objectives of safety validation, covered in ISO26262-Part Clause 8, are twofold. First, to provide undeniable evidence that the safety goals are indeed achieved by the item once it's integrated into the vehicle.
Including.
And second, to confirm that the functional safety concept and the technical safety concept were appropriate in the first place for achieving that functional safety for the item.
So it's about real-world effectiveness, not just theoretical correctness. What kind of environment does this validation happen in, and how does it account for the sheer variety of real-world use?
Precisely. It must be validated in a representative context at the vehicle level. This means considering various vehicle types and configurations. A lane-keeping assist system might behave differently in a small sedan versus a large SUV or even a truck. You also have to consider operational variances that might impact the system's technical characteristics, which were initially considered in the hazard analysis and risk assessment. For trucks and buses, for example, where there can be many different base vehicle types and configurations, this representative context is especially important. The validation must also account for foreseeable misuse. For example, a driver intentionally trying to confuse the LKA system and how the vehicle handles such scenarios safely.
And what methods are used for this final critical validation step?
A comprehensive set of methods is applied. This includes repeatable tests with specified procedures and acceptance criteria, such as positive tests of functions, black box testing where you only observe inputs and outputs, simulation, rigorous boundary condition tests, fault injection on the vehicle itself, durability tests, and stress tests. It also involves various analyses like FMEA, FTA, and ETA event tree analysis to ensure no stone is left unturned and all theoretical failure paths are addressed.
Okay.
Crucially, long-term tests and operational use cases under real-life conditions are heavily utilized. This might involve large test fleets driving hundreds of thousands of miles, or blind tests with normal users to gather data from everyday driving scenarios, often with careful limitations in place to ensure tester safety. Finally, thorough reviews of all documentation and results are performed to provide the ultimate assurance. This multifaceted approach ensures that the vehicle's functional safety is proven not just in a lab or on a test track, but in the complex, unpredictable environment of the real world.
So what does this all mean for us? This journey from a high-level safety goal to actual robust vehicle systems seems incredibly detailed, layered, and frankly, quite daunting. How does ISO 26262 Part 4 really bring those abstract functional safety requirements down to earth in a way that's manageable for engineers?
This is truly the core takeaway of this deep dive, and it's what makes Part 4 so powerful. At the system level, The abstract functional safety requirements, those high-level what-ifs about potential hazards and their consequences, are meticulously broken down and transformed into concrete, implementable technical solutions and designs. It's the critical translation step, where the broad safety objectives start to gain tangible form, ready for actual engineering. It prevents safety from being a vague aspiration and makes it an engineering deliverable.
So it's truly the point where the what of safety becomes the precise how.
Exactly. The functional safety concept, or FSC, provides that initial what functions must be safe, what hazards need to be mitigated. ISO26262-Part then takes this what and defines the how at a technical system level. This is where the technical safety concept, or TSC, and the detailed system architectural design emerge. These two elements act as the indispensable bridge between the high-level safety goals and the specific engineering tasks. This involves specifying precise technical safety requirements, defining exactly how safety mechanisms will be implemented to detect and mitigate faults, and then meticulously allocating these responsibilities to specific hardware and software components. It's a granular decomposition that ensures nothing is left to chance, ensuring consistency and traceability from the highest safety goal down to the smallest component.
And it's not a one-way street, is it? There's clearly a lot of feedback and iteration in this process, almost like a constant dialogue between design and analysis.
Absolutely.
Yeah.
The process isn't linear, it's inherently iterative. As you move from the initial concept to the detailed system design, findings from the rigorous safety analyses and verification activities continually feed back into the design process. This leads to essential refinements in both the design itself and the associated requirements. For instance, if new hazards are identified during these detailed analyses that weren't caught in the initial concept phase, they can and must lead to updates in the initial hazard analysis and risk assessment, or AHERA, from ISO 26262-Part.
Updating the HERA again.
Yes, this iterative refinement ensures a robust, closed-loop development process where safety is continuously assessed, reinforced, and improved upon, ensuring any systematic faults or overlooked risks are caught early, rather than manifesting late in the development cycle or, worse, in the field.
So after all this meticulous work in Part 4, what are the tangible outcomes? What do engineering teams actually produce at this stage that moves the project forward?
This phase culminates in highly detailed specifications that become the practical instructions for the next stages of development. These are not just abstract documents, they are the concrete blueprint. We're talking about the comprehensive technical safety requirements, the detailed system architectural design that lays out the entire system structure, and the crucial hardware-software interface, HSI specification, that acts as the communication protocol between hardware and software.
The blueprints in the rulebook.
Exactly. These documents are the precise, auditable instructions that guide the actual development of the hardware and software. Furthermore, the rigorous testing and validation conducted at various integration levels, hardware, software, system, and vehicle, provide tangible, auditable evidence that those conceptual safety goals have been successfully translated into a safe, functioning product. It's the documented proof that safety is designed in, not just bolted on.
And for someone listening, perhaps a project manager looking at timelines and resources, or an engineer new to this, why does this level of detail and rigor in ISO 26262-Part 4 really matter to them on a practical level?
For engineers, this part of the standard provides the indispensable framework for turning abstract safety objectives into real-world manufacturable designs. It ensures consistency, clarity, and most importantly, traceability throughout the entire development process. You can always trace a low-level software requirement back to a high-level safety goal, which is incredibly powerful for debugging, auditing, and future modifications.
That traceability seems key.
It is. For those managing projects, understanding ISO 26262-Part highlights the critical checkpoints and outputs that are absolutely needed to demonstrate functional safety compliance. This isn't just about making safe cars. It's about proving it with a documented defensible process, which is vital for avoiding recalls or liability issues. Ultimately, for anyone concerned with vehicle safety, whether you're building them or driving them, it's the systematic assurance that the vehicles we rely on every day are engineered to protect us from potential malfunctions, transforming theoretical safety into a built-in reality.
What an incredible deep dive into ISO 26262-Part 4. We've moved from understanding its foundational place in the V model, how it orchestrates the entire development flow, to the nitty-gritty of defining technical safety concepts and system architecture. The critical safety analyses that find weaknesses before they ever become real-world problems, and then the multi-layered verification and integration testing that rigorously proves everything works as intended.
It's a comprehensive framework that systematically translates safety objectives into every design decision, every line of code, and every component choice. It ensures that functional safety isn't just a concept, but a built-in reality for road vehicles, meticulously constructed from the ground up through a rigorous, iterative, and verifiable process.
So, as you reflect on this, what's one thing for you to consider moving forward? Think about a recent safety feature in your own vehicle, perhaps something like automated emergency braking or adaptive cruise control. How many layers of these system-level development activities, from concept definition to detailed analysis to multi-stage validation, do you think went into making that single feature functionally safe? The sheer complexity and the incredible rigor required by standards like ISO26262-Part 4 are truly immense, yet entirely necessary for the safety we expect. Thank you for joining us on this deep dive. We hope this exploration has given you a clearer, more informed perspective on the intricate world of functional safety at the system level. Until next time, keep digging deeper.